Okay, so we're on page 136 on the try these ABC, and we're looking at little a. And this is the polynomial that they give us, and they ask us to find the possible real zeros and use the rational roots theorem to do it and the factor theorem to find them. So this is our first attempt at doing the rational roots theorem together. So the first thing we're going to do is we're going to take a look at this guy. And this is our P. All right, the constant is the P. So what we need to do is we need to write down all of the factors of P, like what multiplies to give you 12. So 1 times 12, 2 times 6, and 3 times 4. So we're just going to write them out in order. Now, you don't have to write them in order. I just do that. And keep in mind that for each and every one of these, there's a plus or minus value attached to it. So I'm just going to put my plus or minuses in because it's good for either one. The next thing we're going to do is we're going to look at the leading coefficient on our highest exponent power of 4, which is 1. And this guy is our Q. So we are going to write down all the factors of Q. Well, the good news is the only factors of 1 are 1. So plus or minus 1. So now when we go to write our possible roots, all the ones that could possibly work, we have to put P over Q. So I'm going to save a little space and put it over here. So all the P's over all the Q's. So essentially what this looks like is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12, all over plus or minus 1. And the good news is that anything divided by 1 is itself. And the signs kind of opposite each other, which means that you're going to end up with a plus or minus anyway. So our possible roots, these are all the possible real roots that will potentially work, is just 1, 2, 3, 4, 6, and 12. If you're wondering why we have to use the Q at all, it's because sometimes this leading coefficient isn't a 1, and then there are a lot more combinations. So hang tight. We are going to get to those, but I didn't want to do that on the very first one. So these are all of our values that are possibles. Now what we're going to do is we're going to go into the factor theorem, and we are going to test these and find the ones that work. Now remember that for factor theorem, what you need to do is you need to substitute in the value into the function wherever there's an x term and see if your remainder is 0. If you get a remainder for 0, that means that it's a factor, or not a factor, it's an answer, it's a root, and that's a solution. So the first one we're going to test is x equals 1. This is the part that gets a little tedious, and which is why I'm showing you a whole different method of doing this today. All I'm doing is substituting 1 into my function up here. And wherever I get an x, I'm just putting a 1 to test it. Now I'm going to do something real crazy, and that's just type it into my calculator, and then I'm going to keep revising my numbers to go faster. So I know I can calculate this with 1s, but I'm actually just going to recopy, and that's going to help me for the bigger ones. So 1 second. So I can set us up for success for the rest. Okay, so I literally typed it in exactly as I wrote it. I'm going to hit enter, and I get 8. So 8 is my answer. Because this is not 0, then that means this is my remainder. So this is not a solution. Okay, it's got to be 0 for it to be a solution. So 1 doesn't work, so we're going to try -1. And what is cool about this is, if I go to the calculator, if you have a fancy one like this one, or like the scientific one that does this, you can copy your entry over and go back and insert a -1. Insert a -1. Insert a -1. And you get 0. Look at that. So when I plug -1 in here and calculate, I get 0. So what I'm going to do is I'm going to take this guy and highlight him. This is a solution. I know it's a solution because the remainder is 0. Okay, so x equals 1 is one of my answers. Now it's a fourth term, or it's a fourth degree, which means that there's going to be 4 answers, potentially. So we're going to keep going. We're going to take a look and see if 2 works. So going back to this, we're going to plug 2 in. You can see how tedious this is. That's why I kind of like using the calculator, because I can copy it over and put in 2. I'm going to put in -2 first because the negative is already there. So -2, -2, -2, go. Oh, that gives me -16. So I'm just going to change these to negatives. And this is a -16, so that's not a solution. We want 0 for a remainder here. So let's go back through and take the negatives out. Zero. Boom. Okay. So we found our second one. So when I put 2 in, just regular 2, you get 0, and that is a solution. Boom. There's our second one. So you're going to continue to do this. Keep trying. All right, so we did +1, -1, +2, -2. We're going to keep on going until we end up with 4 solutions. I'll be back with your final answer here. Woo, okay, so it looks like this magically appeared to you, but it took me about 5 full minutes to get the rest of these done. I went through and I substituted in every single possible root from our list, and I only got one more solution, and that one was at x equals -3. Now, because our polynomial is a 4th degree, it can have up to 4 real roots. This one only has 3 real roots. So that means that our 4th root could potentially be a square. No, it can't be a square root. Our 4th root has to be a double of some sort in here. We'll explain why it can't be a radical or why it can't be imaginary a little later. But for right now, we have 3 real roots, which means one of these is a double, which means it's going to bounce somewhere. Okay? So this is how you do the rational roots theorem and how you use it to find the roots. Now, this is very inefficient. Okay, and the reason why I'm showing you this is because when we do synthetic division, this is going to go a ton faster. So I just want you to know that this is an option, but this is a long option. Okay, so I'm going to stop this one and we're going to take a look at another one.